Welcome to this part of the RC analysis. We are given with three circuits in which we have to find the output waveform, and here the Vn is step input of amplitude V1 volts. Okay, let's get started with the first question. So in order to find the output waveform, here we are going to go through the same steps just to find the V out at t is equal to 0 and at t is equal to infinite. So let's get started with the finding the V out value at t is equal to 0. So here, for instance, let us consider V out does not jump. Okay, so what does that mean? That means Vc1 is equal to the Vin. Here Vc1 is the voltage across the capacitance, and what is the current that is flowing through the capacitance? In order to find that, we'll use the equation of capacitance, which is Q is equal to Cv. And if you do derivative on both sides, the derivative of Q with respect to time is current, and here C is constant, and this is dV by dt. As you can see, Vc1 is the voltage across the capacitance, and derivative of Vc1 with respect to dt here is d of phi V1 times u of t divided by dt times C is equal to the current, and here this is equal to C V1 delta of t. Okay, if you try to plot this image here, it will be like this, of amplitude C V1 times delta t. So this is the graph, and if you see this is a infinite current. Infinite current, right? So if an infinite current flows through the capacitance, then its voltage jumps instantly, and this current, it flows through this second capacitance also. So what is the equivalent circuit of this given circuit is at t is equal to 0. This has just two capacitance in series. This is C, this is C. We have to find V out here. This is V in here. Okay, this thing here is capacitance voltage divider circuit. This is capacitor voltage division circuit. And what is the V out of this circuit? Okay, now that we have found the value of V naught at t is equal to 0, which is V naught is equal to, here as we have assumed the values of C1 and C2 to be C, it comes out to be V1 divided by 2. Okay, now we have to find the value of V out at t is equal to infinite. So at t is equal to infinite, this capacitance over here discharges all the charges that is present in it across this resistance. And what this capacitance does, it tries to get charged through this resistance with the help of this Vn voltage. So it charges till the voltage across C reaches V1. So Vc1 here becomes 0 and V out becomes V1, or you can say that C2 charges to V1 volts. Okay, now we are ready to plot the output waveform. So which is, this is the time axis, this is V out, and at t is equal to 0, this is at V1 by 2, and at t is equal to infinite, this thing is V1. So it starts from here and reaches till this point. This is V1 and this is V1 by 2. Now we have to find the time constant. Time constant here is parallel combination of capacitance multiplied with the R. So parallel combination of capacitance, in the sense it is 2C times R. This is the time constant. Okay. Now this question can also be solved using another approach. So I will be discussing that approach now. This is one of the easier way of solving the same question. At t is equal to 0, if there is a parallel combination of capacitance and resistance, you can always assume this circuit as a single capacitance of same value. And if there is a series combination of resistance and capacitance, you can assume that to be equal to a single resistance of the given R value. And at t is equal to infinite, these parallel combinations can be assumed to be a single resistance. And in case of series combination, you can assume this as to be a single capacitance. The proof of this approach, I'll be discussing that in upcoming videos, so don't worry about that. So going back to our question, now I will be solving the second question using that alternative approach. Okay, so now at t is equal to 0, what I have said is that this capacitance remains the same and this parallel combination becomes a single capacitance of the same value as given here. So this thing comes to be C V and V out. So now, as I have said earlier, this is capacitance voltage divider circuit. So what is the V out in this case? V out is equal to V in C1 times C1 plus C2. As the values of C1 and C2 is same here, this comes out to be Vn by 2, which is equal to Vn by 2. Okay, at t is equal to 0, V out is equal to V1 by 2, right? And at t is equal to infinite, the equivalent circuit is this. This thing is just a resistor here. And what about the capacitance that is present here? Because at t is equal to 0, this capacitance acts as a short circuit, so we have considered that here. But at t is equal to infinite, this thing is open circuited, right? So what is the voltage across this thing? The voltage across the resistance, this is Vn. So this thing is equal to 0, right? Because by applying KVL here, this thing is Vn minus Vc is equal to V out. Vc becomes Vn as it gets charges through the resistance here. So V out is equal to 0 in this case. Okay, now we will plot the output waveform. This is the time axis, this is V out, and at t is equal to 0, this thing is V1 by 2, and as time goes on, this thing becomes 0. So this is V1 by 2. Okay, and the time constant remains the same. This is parallel combination of capacitance with multiplication of resistance. Okay, this is the time constant. And moving on to the third question, we will follow the same procedure. At t is equal to 0, we draw the equivalent circuit, which is C and R here, V out plus minus V in. At t is equal to 0, initial charge across the capacitance is 0, so the voltage across the capacitance is also 0. Okay, and at t is equal to infinite, the equivalent circuit of this thing is just a resistance, right? R, this is V out, this is V in. So V out in this case is just voltage divider circuit, so which is V in divided by 2, which is equal to V1 by 2. This is your V out. Now we will plot the output waveform here. This is time axis, this is V out. At t is equal to 0, it is at 0, and t is equal to infinite, V out is V1 by 2. This is V1 by 2. And tau here is parallel combination of R times C. This is your time constant. Okay. Thank you for watching this video. We'll meet soon in the next video.